Okay, so today we are happy to have Pooneh Afsharijoo, and she will talk about two new members of Rogers-Ramanujan Identities.
Thank you. I would like to thank first the organizers for this invitation. As you said, today I will talk about the integer partitions and the identities between them, especially the Rogers-Ramanujan identities. I start my talk with the definition of a positive an integer partition of a positive integer n, which is a sequence of decreasing positive integers whose sum is equal to n, and we call them the parts of our partition. If lambda is a partition of n, I will denote it by lambda 2.n. I will denote the number of parts of our partition by L of lambda, and the total number of partitions of n by P of n. By convention, 0 has one partition, which is empty set. For example, 4 has following partitions: 4, 3 plus 1, 2 plus 2, 2 plus 1 plus 1, and the last one is this partition. So P of 4 is equal to 5. Now, what is a partition identity? A partition identity is an equality between the number of partitions of n satisfying some property P1 and the number of partitions of n satisfying another property P2, which is true for every n. This type of identities play an important role in many areas like number theory, Lie theory, statistical physics, and so on. And my research is based on this type of identities. Our first method to find such an identity is using the commutative algebraic tools and algebraic geometrical tools. Our bridge from partitions to commutative algebra is Hilbert-Poincaré series, which are defined as follows. Let's take a field of characteristics 0k and a k graded algebra A, where an is finite dimensional. Then the Hilbert-Poincaré series of A is this Q series. Dimension of an times q to the power n. Maybe the first relation that we can see between the Hilbert-Poincaré series of the graded algebras and the generating series of partitions is where we take S as k of x1, x2, and so on, which is graded by weight of xi equal to I. Then we can see that Hilbert-Poincaré series of S is equal to the generating series of Pn, which is equal to this infinite product. Actually, this equality comes from the fact that to each monomial, let's say x lambda of S, where lambda 1 is the greatest one, we can associate a unique partition lambda 1 till lambda m of sum of lambda i's. So we use the Hilbert-Poincaré series of the graded algebras to find the partition identities. But the graded algebras that we used to do this comes from an important algebraic geometrical object, which is arc spaces. I will define it just for the case that I will use today here. So we take an algebraic variety x defined by the polynomial f in k of x, where f of 0 is equal to 0. The arc space of X, which is denoted by X infinite, is the set of formal power series on one variable t, such that f of x of t is equal to 0. Since if x of t is a formal power series on t, so I can write it as x0 plus x1t plus x2t squared and so on. And if I replace this notation in f of x of t, I will obtain again a formal power series on t, where the coefficient fj of t to the power j is in k of x0, x1, and so on. But as you know, I want to work with the partitions, and we know that the parts of a partition can't be equal to 0. So we are interested in the case where x0 is equal to 0 in big fj's, and we define small fj's as follows. And this gives us an algebra, a graded algebra, which is called the focus arc algebra of X. We denote it by J0 infinite of X, and it is defined as S over the ideal generated by small fj's. And note that for each j, fj is homogeneous of weight j. This is the Hilbert-Poincare series of this type of graded algebras that helps us to find the partition identities with our methods. But before seeing how does it work, let's fix some notations. Let's take a monomial ordering on S. For each polynomial of S, we define the initial part or initial term of S like its largest monomial. And for each ideal of S, we define its initial ideal, which is the ideal generated by the initial parts of its polynomials. And finally, we define a Grobner basis of I with respect to this monomial ordering, which is a non-zero set of polynomials of I whose initial term generate the initial ideal of I. Now we are ready to see how our method works to find the partition identities. One of the most important identities is a family of partition identities, which is called Gordon's identities. The theorem says that if we take the integers r greater than or equal to 2 and I between 1 and r, we denote by Bri of n the number of partitions of n with at most I minus 1 parts equal to 1, and such that if we take a block of r parts of our partition, the difference between the first and the last part of this partition be at least equal to 2. And we denote by a Ri of n the number of partitions of n whose parts are not congruent to 0 and plus minus I modulo 2r plus 1. Then these two numbers are equal for every integer n. The analytic form of this theorem is says that this Q series, this big Q series, is equal to this infinite product. And actually, in the right-hand side, we have the generating series of A Ri of n, and in its left-hand side, we have the generating series of B Ri of n. So let's see a special case of this theorem where r equal to I equal to 2. In this case, B22 of n comes the number of partitions of n. Here I have to replace r by 2. So I have bj minus bj plus 1 greater than or equal to 2, which means that B22 of n counts the partitions of n without equal or consecutive parts. And so we can't have more than one part equal to 1. And in the other side, A22 of n counts the number of partitions of n whose parts are not congruent to 0 and plus and minus 2 modulo 2 times plus 1, which is 5. Or equivalently, where aj is congruent to 1 or 4 modulo 5. So let's see this special case of Gordon's identities in the partitions of 4. We have B22 of n and A22 of n, and the partitions of 4. I will denote this type of partitions by the partitions of type 1. The first partition of 4 has just one part, so obviously it is a partition of type 1. In the second one, we don't have any equal or consecutive parts, but in the other partitions, we have at least one pair of equal parts. So we have just two partitions of type 1. I will denote this type of partitions now by the partitions of type 2. Obviously, the first partition is a partition of type 2. In the next three partitions, we have at least one part which is not congruent to 1 or 4 modulo 5. But in the last partition, we have all parts are congruent to 1 modulo 5. So again, we have two partitions of type 2. But note that if we fix the length of partitions, the theorem is not true anymore. For example, we have a partition of type 1 and length 2, but we don't have any partition of type 2 and length 2. Actually, this is a special case of Gordon's identities when we take R equal to I equal to 2 is an important case which is called the first Rogers-Ramanujan identity. It was found by Rogers and Ramanujan separately, and if we take R equal to 2 and I equal to 1 in Gordon's identity, we found the second Rogers-Ramanujan identity. With Hussein Muqtada, we found a family of this type of identities. The theorem says that if we take the integers n and k, the number of partitions of n whose parts are at least equal to k without equal or consecutive parts is equal to the number of partitions of n whose length is at most equal to its smallest part minus k plus 1. Note that if I take k equal to 1, in the first slide, I have exactly B22 of n of Rogers-Ramanujan identity, the first Rogers-Ramanujan identity. It's why we called it the case Rogers-Ramanujan type identities. And in the second side, we have the partitions whose length is at most equal to its smallest part. This gives us, in this case, if I denote it by C22 of n, a new member of the first Rogers-Ramanujan identity. Before proving this theorem, let's see the theorem again in the partitions of 4. So as I said before, I will denote by C22 of n, the number of partitions of n whose length is at most equal to its smallest part. And I denote this type of partitions by the partitions of type 3. In the first partition, the length of partition is equal to 1, and its smallest part is 4, so it is a partition of type 3. In the second, fourth, and fifth one, the smallest part is equal to 1, which is not greater than or equal to the length. So they are not the partitions of type 3. But in the third one, the length and the smallest part are both equal to 2. So it is again a partition of type 3. And note that even if I fix the number of parts, the theorem will still be true between B22 of n and C22 of n. For instance, we see it just for the partitions of 4, but later we will see it for every.
If I may interrupt you, there's a question in the chat. So it's asking, is there a natural bijection between the two kinds of partitions of n in Gordon's theorem? Can you say something about that?
No. Actually, even if for the case r equal to 2, for the Rogers-Ramanujan identity, we couldn't find a bijection yet. It is a big open question.
Mm-hmm. Thank you.
You're welcome. For proving this theorem, we proved it first for the case k equal to 1. We took by our first method, we took the algebraic variety x squared in k of x, and then we defined a k derivation d on s by d of xi equal to xi plus 1. And then we computed the focus arc algebra of x, and we observed that the ideal which defines this focus arc algebra is a differential ideal generated by x1 squared and all its iterated derivatives. I will denote it here by I2, and then we used a result of the paper arc spaces and Rogers-Ramanujan identities of Bruchek, Muqtada, and Shepard, which say that if we denote by IR the differential ideal generated by x1 to the power r and all its iterated derivatives, then the initial ideal of IR with respect to the reverse lexicographical monomial ordering is generated by these monomials. In our case, R is equal to 2, so the initial ideal of I2 with respect to the reverse lexicographical monomial ordering is generated by xi squared and xi plus 1 for I greater than or equal to 1. Then we used an important theorem which says that if I is a homogeneous weighted ideal of S, then its Hilbert-Poincare series is equal to the Hilbert-Poincare series of its initial ideal with respect to any monomial ordering. We applied it to I2 and reverse lexicographical monomial ordering for I2, and we have this equality. But note that by the definition of this initial ideal, the monomials which appear in this algebra are those which are not divisible by xi squared or xi plus 1, which means that the partitions that we can associate to this algebra are those without equal or consecutive parts. In other words, the partitions which are counted by B22 of n. This proves that this Hilbert-Poincare series is equal to the generating series of B22 of n. And by the analytic form of Gordon's identities or Rogers-Ramanujan identities, it is equal to this Q series. In order to find a new member for the first Rogers-Ramanujan identity, we wanted to use once again this theorem, but this time we wanted to apply it to the initial ideal of I2 with respect to the lexicographical monomial ordering. So the first question was to find this initial ideal or find a Grobner basis of I2 with respect to the lexicographical monomial ordering, and then finding the partitions that we can associate to this algebra. But we proved that such a Grobner basis is not differentially finite, which means that we can't find the finite number of polynomials of S such that I2 be generated by these polynomials and their iterated derivatives, and that the initial ideal of I2 be generated by the initial parts of these polynomials. And so we couldn't find this Grobner basis completely, But we found a part of these Grobner bases using Buchberger's algorithm. And then we generalized this part, and we had a candidate for this initial idea. I denoted here this candidate by J, which is generated by xi1, xi2 till xik times xk. And then we computed its Hilbert-Poincare series directly using Hilbert-Poincare series properties, and we proved that it is equal to this Q series. But remember that the right-hand side, this Q series is the generating series of B22 of N, of the first Rogers-Ramanujan identity. And in the left-hand side, note that to each generator of J, I can associate a partition lambda as lambda 1, I1 till ik and k. The length of lambda is equal to k plus 1, which is strictly greater than its smallest part. This means that the partitions that we can associate to this algebra are those whose smallest part is at least equal to its length. Or in the other words, the partitions which are counted by C22 of N. So this proves that the Hilbert-Poincare series of S over J is equal to the generating series of C22 of N, and this proves that C22 of N is a new member of the first Rogers-Ramanujan identity. In order to prove our theorem for the other cases, for the k greater than or equal to 2, we played the same game, but this time we used the differential ideal xk squared and all its iterated derivatives, and we did the same. This proves our theorem in other cases for the other identities of our family of identities. Note that in this theorem, we started by an important object of the algebraic geometry, which was arc spaces, and then we used the commutative algebraic tools, the Hilbert-Poincare series, to find a combinatorial result, which is an identity between the partitions. After this theorem, I proved another theorem which proves the case k equal to 1, the previous theorem, and which proves that even if we fix the length of partitions, the theorem will be still true, and also which adds a new member to the second Rogers-Ramanujan identity also. So I will denote by C22 of Mn the number of partitions of n with exactly m parts whose length is at most equal to m, and by C21 of Mn the number of partitions of n whose with exactly m parts whose length is strictly less than lambda m. Then I take sum over m of C2i of Mn, and this gives us a new member of the both Rogers-Ramanujan identities. In order to prove this theorem, I used another method which is completely combinatorial and which was used in George Andrews' books. Andrews, in his book, the integer partitions, the theory of partitions, he denotes by small b2i of Mn the number of partitions of n with exactly m parts without equal or consecutive parts. And then he proved that b2i of Mn verify this system of recursion formulas. And not just that, he proved that B2i of Mn's are uniquely determined by this system of equations. What I did to prove this theorem was that I proved that C2i of Mn also verify the same system of equations. For the first equation, it is trivial because we know that 0 by convention has just one partition of length 0, which is empty set. The negative numbers don't have integer partitions, and the positive numbers don't have the partitions of length negative. So C2I of Mn also verify the first equation of this system. In order to prove the second one, note that if I remove the partitions which are counted by C21 of Mn from those which are counted by C22 of Mn, what remains is the partitions with exactly m parts and whose smallest part is exactly equal to m. I transform such a partition to a partition by removing m from it. So I will obtain a partition of n minus m with exactly m minus 1 parts, whose smallest part is strictly greater than its length. So it is a partition which is counted by C21 of m minus 1 and n minus m. And since it is a bijection, this proves the second equation for C2I of m. In order to prove the last equation of Andrew's system for C2I of Mn, again, if we take a partition which is counted by C21 of Mn, and this time I transform it by removing 1 from each part. Again, I will obtain a partition of n minus m with exactly m parts, whose smallest part is at least equal to its length. And it is again a bijection and proves the last equation for C2I of Mn. And since P2I of Mn are uniquely determined by Andrew's system, so actually we prove that C2I of Mn is equal to P2I of Mn. This proves that even if we fix the length of partitions, the theorem will still be true, but we have seen for the partitions of 4, but now we have it for every n. And if we take the sum over m, in the right-hand side, we have the sides of Rogers-Ramanujan identities, and in the left-hand side, we have a new member for these identities. And this proves our theorem. After this theorem, I proved another theorem which adds another new member to Rogers-Ramanujan identities, which behave differently on even parts and on odd parts of a partition. So let's regroup the even parts of a partition lambda and denote them by lambda I else, and its odd parts by lambda j else. The theorem says that if we denote by P2I of n the number of partitions of n with at most I minus 1 parts equal to 1, whose smallest even part is at least equal to 2 times the length of lambda, and whose odd parts verify this inequality, which means that if we take a block of 3 odd parts, then the difference between the first and the last part of this block is at least equal to 4, then P2I of n is a new member of Rogers-Ramanujan identity. Again, before proving this theorem, let's see the example in the partitions of 4. I take here I equal to 2. The first partition of 4 has not the parts equal to 1. His smallest even part is equal to 4, which is greater than 2 times its length, and it has not odd parts. So if I denote this type of partitions by the partitions of type 4, we have the first partition as a partition of type 4. In the next partition, we have just one part equal to 1. We don't have any odd parts, and we don't have any block of we don't have any even parts, and we don't have any block of 3 odd parts. So it is again a partition of type 4. In the next 2 partitions, we have 2 as the smallest even part, which is not greater than or equal to 2 times the length. And in the last one, we have more than one part equal to 1. So again, we have 2 partitions of type 4, and again, even if we fix the length of partitions, the theorem will still be true. In order to prove this theorem, I used a third method, which is again combinatorial. This time I create a new system of recursion formula, and I proved that P2I of Mn verify this system and are uniquely determined by this system. And note that proving that P2I verify this equations is not trivial and is not easy, like as we saw earlier for C2I of Mn. And then this time I proved that B2I of Mn also verify this system of equation, and as before, we have equality between these two numbers, and if we take sum over m, in the right hand side we have the sides of Rogers-Ramanujan identities, and in the left hand side we have a new member for these identities, and this proves this second theory. I think that I have some more time, so I would like to talk about Gordon's identities also. Once we found the new members to Rogers-Ramanujan identities, we were interested in to find a new member for Gordon's identities also, which is the for the Gordon's identities also, and we used our first method to do this, and we had a candidate, and then I conjectured a new member for Gordon's identities. To introduce this new member, I defined a new classification of parts of a partition. So let's take the integers r and I and L between 1 and R. I will denote the L's new part of lambda by pi L of lambda. The first new part is just the smallest part of lambda. Between 2 and I is lambda m minus the previous new parts, and after I is lambda m minus the previous parts plus L minus I. If in our computations we found some lambda j for some j, some negative j, then we will take it equal to 0. And once we found a new part equal to 0, then all other next new parts also will be equal to 0. For example, if I take I equal to 2 and R equal to 5 and this partition, so the length of this partition is equal to 5. P21 of lambda by definition is the smallest part, which is equal to 2. P22 of lambda, we are here, so it's lambda m minus previous new part, lambda 3, it is equal to 3. P23 of lambda is, now we passed here, it's lambda 5 minus previous new parts plus 3 minus 2. It is equal to lambda 1. It is equal to 6. The next one is lambda m minus the previous new parts plus 4 minus 2. It is a negative number, so we will take it equal to 0, and then the next new part also will be equal to 0. By this definition, I conjectured a new member for Gordon's identities, which says that if we denote by CRI of n the number of partitions of n with at least one new part equal to 0, then CRI of n is a new member of Gordon's identities in general. We already see the proof for the case R equal to 2 for the Rogers-Ramanujan identities. For R equal to 3, also I proved it with the second method with Andrew's system. And note that Andrew's system has R plus 1 equations for R. So for 3, we have 4 equations there. And proving that C3I of Mn verified the third equation was not at all easy, like the case R equal to 2. But for the case R greater than or equal to 4, I couldn't prove it before my defense. But after my defense, we proved it with Joan Douze, Frédéric Rouet, and Hussein Murtada. And now we know that CRI of n is a new member of Gordon's identities. I think that I will stop here, and thank you for your attention. Thank you.
Okay, so thank you for the very nice talk.
Thank you.
So there's some time for question now. So there was already a question in the chat. So maybe let me ask that question first, and then we can see if there's other questions. So the question in the chat is, does the sequence A22 of n have other interpretation in the integer sequence database other than those for P22n and C22n?
Yes, but if I understand well, you mean that if there is another new member for Rogers-Ramanujan identities, and we saw already that the question is the answer is yes, because we have P22 of n, which is a new member also, and so its generating series is equal to the generating series of A22 of n.
Yes, I'm sorry. I was the one asking the questions. No, what I meant is that, is there anything known before the sequences that you discover in this paper?
Okay.
And also, can you just list the first 5 or 10 numbers for A22?
Okay.
For n equals 1 to 10, let's say.
Okay, as you.
I mean, so that I could actually take it and type it into the database and check.
I don't think that you can do it because it's not. I mean, I know that there is another member of Gordon's identities, which was found
No. I don't. Well, I'm not saying the very general Gordon. Okay.
Just for Rogers-Ramanujan.
Yeah. Right. Just let's say just for the 2-2 case.
Okay.
Also, is there any closed formula in terms of, let's say, some binomial coefficients and things like that for these sequences?
Yeah, as I know, I think that the answer is no, but I'm not sure.
Oh, okay.
Are there any other questions, comments?
I have a question. So how do you get this A22 using Hilbert-Poincaré series? So for example, for B22, you considered reflex ordering, right? So for A22, how do you get it?
For A22 is even easier than that, because if I, sorry, what's happened with, okay, A22, I will come back to Rogers-Ramanujan identities. Okay, A22 of n is this number. So it counts the number of partitions of n whose parts are congruent to 1 or 4 modulo 5. So if I want to associate an algebra to these partitions, this algebra will be K of xi, where I is congruent to 1 or 4 modulo 5. And then Hilbert-Poincare series of this algebra is equal to the generating series of A22. But we can't use our method. I know what you mean. You mean that if we take I2 and if we see its initial ideal with respect to some monomial ordering, what is the monomial ordering that we can take for finding the generating series of I22? But it's we don't know yet the answer for this question.
Okay, thank you.
Okay, may I ask some more questions?
Sure.
Given a Hilbert-Poincare polynomial,
Yes.
all right, there are usually many ideals that have that same Hilbert polynomial, right?
Yes.
So, so you pick some very special ideals, and you show that because they have the same thing, so therefore their counting sequence are the same. Can you do that for arbitrary kind of ideals that have the same Hilbert polynomial?
Yes. And so I didn't think about it, but I'm not sure. Maybe we can do it, but I have to think about it. I don't know. I can't answer you now.
And then of course there's the more general question that so you pick one particular generating function, the q forgot about that, something over 1 minus q and all that, right? What about other kinds of other forms of other Hilbert-Poincare?
Yeah, so we always start by with arc spaces, and then we found the ideal which is connected with this arc space. And now you will ask for the other side. If we have the Hilbert-Poincare series, or if we have Q series, can we find an ideal and then do this same things that we did here? These questions I didn't think about neither, but our method is always in the other side. We start always with the arc spaces, and then we find Hilbert-Poincare series, and then we use its initial ideal.
Okay. I'm not very sorry. Never mind. Go on.
Okay, so maybe it's now a good time to move to the breakout room. So let me stop the recording.